This conference will now be recorded.
Okay, perfect. Good morning, guys. Thank you for joining me this morning. I'm sorry to take, the time is 5:15 now. The updates on my Mac were pending and things were going in the background and I couldn't open the PowerPoint. That was the reason. Okay, putting things aside, let's start off. Yesterday, we have discussed about various important aspects of training the models, and we discussed about the learning curves, what happened at various aspects what are the things you need to observe in the learning curves. And I also explained you about what is polynomial regression, how things will work in polynomial regression. In the polynomial regression, we discussed about 3-degree, 100-degree polynomial regression, and how you can understand the performance of a model on top of that. Okay, so the next thing is we also have done an evaluation and performance of the model on the training set, and what happens if new set of features are added to the existing training set, and how does the error looks up when you are dealing with the training set. This is the one diagram. You have root mean square error on the y-axis, and you have training set on the x-axis. Here I have explained about what is learning curve, how you generate plots, and what you can analyze from the learning curves if you implement the linear regression model. Okay, and what is the underfitting and overfitting was I explained you. Now, you guys, you need to really revisit, memorize, take a pen, draw a flowchart of each and every topic. If you carefully observe what we have done in a linear regression, how we have trained a model, how we have found the errors, how we did the validation, that's one set. And after that, we did the same thing for logistic regression. We did the same thing for the polynomial regression. If you clearly memorize what we have done, then it will be very easy for you to go and implement the whole flow. Okay, that is what it is. Now let's understand the bias and variance trade-off. Now, hope you're able to see my screen and I believe my voice is audible. This is one important aspect to understand bias and variance trade-off. This question is asked in every interview I go. What is bias and variance whereof? What is confusion matrix? And how do you deal with the bias and variance trade-offs? How do you deal with confusion matrix? This kind of questions have been asked everywhere I go to the interview. So understand the concepts and implement them carefully. Now, why do you use bias and variance? What is bias and variance trade-off? What is bias? What is variance? What is the difference between them? And what is the trade-off point? Okay. First thing we need to understand is, there is a concept called underfitting and overfitting. Okay. Overfitting means your model is so simple that it performs really well on the training data, but it generalizes and throws error messages on the test data. Okay. Underfitting means your model is so complex that it gives you a different predictions on the training data and test data. Now, how do you solve underfitting and how do you solve overfitting? How can you be how can you reach the point where it is not overfitted, it's not underfitted? Okay. Now, one way to improve your overfitting model is to feed it more training data. How long do you feed? Until the validation error reaches the training error. Now, what is a training error? It's root mean square error or mean square error. Once again, when you are dealing with root mean square error or mean square error, understand the function which is capable of doing mean square error will also be able to do the root mean square error. So do any function. Again, what are those functions is what we have explained earlier, the normal equation, n1 form, n2 form, and all these things. Let's not get diverted into that one. We'll compare this concept and then move into that concept. Okay. Now, one way to improve the overfitting model is Feed it more training data. Perfect. When you say feed more training data, it's not just adding new features. It's about adding the whole new data until a validation error reaches the training error. Makes sense. Now let's jump into the bias and variance trade-offs. A model's generalization error can be expressed as the sum of three very different errors. What is generalization? What is generalization? Generalization is nothing but one thing to say is in machine learning, your model is generalizing a lot. What does it mean? Actually, it is giving the prediction without learning from it, and it's learning from it, it's just generalizing it. Okay, that is the difference. Generalization is very simple. It's telling you generally without learning, which we don't want. We want machine to learn from several examples. We want machine to learn from an experience. We want machine to learn by itself and give us predictions. Okay. So always remember when somebody is asking you about generalization, tell them, boss, generalization is all about how effective your algorithm is. Is your algorithm learning by itself and giving the predictions, or is it generalizing the predictions? So people talk it as an ability of an algorithm for an effective way of learning an algorithm by itself across the range of inputs and applications. I can give an example for this because the generalization, normalization terms confuse you a lot. So kindly, uh, pause there when you are confused and then get a clarity and then move on. Now, we have worked on an example classification of images number 5. Perfect. First time you correctly identified 5. Now, will that 5 still be 5 if I put the number 5 up and down? What I mean to say is, first time you identified number 5 perfectly. Okay. Now what am I saying is, I'm saying to identify number 5 after turning it like this. This is the other way around of 5. But actually now this is 2. If I turn it, if I do the upside down, the 2 becomes 5. Okay. Now with this example, what is happening is when I move the 5 up and down, okay, would you still be able to identify 5 as 5? No, right? You will say the second one as 2. Now, this is because you know that generally 5 looks like this and 2 looks like this. But how does machine know that this guy has turned 5 upside down and asking me to identify it as 5? Okay, now that is called generalization. The machine learning will be able to achieve this performance in certain fields. If the underlying algorithm, which is not effective in any other field, will have a problem. But generalization with best abstract features will have the ability to learn from it and come back. So long story short, generalization is nothing but the way your model is generalizing and not learning. If again go back and memorize your banana, apple, what did I say yesterday? Banana, apple, and orange in one, and banana, apple, orange, strawberry, and grape in another one. Okay, that is what it is. Now, a model generalization error can be expressed sum of three different errors. Sum of three different errors. One is bias, one is variance, other is irreducible error. The bias variance trade-off is called as bias error. This error is due to wrong assumptions. What is the wrong assumptions? Assuming that the data is quadratic, assuming the data is linear. Actually, there is no really linear relationship in the data, but you assume that it is a linear data. Problem number one. Problem number two, when it is actually quadratic. I explained you what is quadratic, so I don't want to waste time on that. That is the reason where you get BIOS issues. So the BIOS variance trade-off is BIOS error. This error is due to wrong assumptions. The wrong assumption is you think the data is linear when data is not. And second part is when it is actually quadratic. A high bias model is most likely to underfit the training data. Now, the other way you can remember this for a long time is bias will underfit, variance will overfit. Simple. BIOS is underfitting, variance is overfitting. In BIOS, the generalization will be very high, and in overfitting, the model is too complex. Okay, you need to use some other models to come with the best predictions and reduce the errors. Okay, hope you are clear with this point. Now, let me take a pen, let me move to pointer and go back to the next session, next screen, next screenshot. Now, hope you are clean with this. Now, BIOS variance trade-off variance. Guys, try to understand. Here you are talking about BIOS variance trade-off BIOS error. Okay, let me highlight this one. Okay, here you're talking about BIOS variance trade-off variance. Okay, now let's understand what is variance. Now, this is nothing but a model with many degrees of freedom. When I say many degrees of freedom, you have seen polynomial 300 degree, polynomial 10 degree, and linear regression. We compared three of them. Okay. When you take a high degree polynomial model, it is likely to have high variance and thus overfits the training data. Makes sense. Now let's understand the bias variance trade-off irreducible error. Irreducible error is the error that cannot be reduced. Okay, now this error is due to noisiness of data itself. Again, what is noisiness? Noisiness is, first you have given me apple, banana, orange. I found it really well. And now you gave me a new data which I've never seen in my lifetime, and I would have to work really hard to sense and understand what is that. Okay. The only way to reduce this part of error is to clean up the data. How do you clean up the data? How do you clean up the data is nothing but fix the data from data sources, fix the data with the broken sensors, or remove the outliers. When I say broken sensors, again the missing values, your your what we call applying the imputer, applying the various I don't remember on top of my head, but you know what we have done earlier in cleaning the data and sorting out the data as part of data pre-processing. So that is one thing you need to do. So you understood about bias, you understood about variance, you understood about what to call the irreducible errors in bias and variance trade-off. If you have questions, please stop me here. Okay, let's move on to next slide. Now, how do you increase the model's complexity? Again, guys, your variance is all about your model's complexity. Your bias is about your model generalizes the data very well. Generalizing is it's not learning and giving the generalized errors. Okay, now increasing a model's complexity can be done by increasing its variance and reducing its bias. Makes sense to me and makes sense to yours. Conversely, if you wanted to reduce the model's complexity, increase its bias and reduce its variance. Look at the uh, what you call comparison. If you want to increase the model complexity, increase the variance, reduce the bias. If you want to reduce the model's complexity, increase the bias, reduce the variance. This is called trade-off. Trade-off means you are at the center of not in falling in bias and not falling in variance. Okay, you are at the between. This is called trade-off. Bias is one area, variance is other area, Trade-off is between that area. Okay, perfect, perfect. Now, are you clear with this one? Did you understand carefully what is bias, what is variance, what is bias, variance, irreducible error, and what is trade-off? Kishore, hope everything is clear till this point. Quick response, please. Okay, perfect. I got it. Thank you. I understood that you are clear. Now, let's understand regularizing the linear models. Okay, I said my model does a lot of generalization when it comes to what? When it comes to learning. When generalization is more, that is bias. Likewise, you have a regularized model. Okay, regularized model is nothing but what is regularization? How do you regularize things in machine learning? That is very important. You need to understand. First of all, the word itself says regularization means it is helping to solve the overfitting problem. Okay, like you have generalization and underfitting, you have regularization and overfitting. When you are performing a data science machine learning pipeline, first you go and understand the data, you visualize the data, you get the average, mean, median, variance, deviation, blah 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 blah, and then you visualize you visualize with the matplotlib and histograms, and you do the pre-processing, like if you have to remove any unnecessary columns, if you have to replace the missing columns, if you have to maintain a checklist, that is done. From that, again, you come up with the best important features that will help you to maintain the best model. That is also done. After that, you are getting ready to prepare the model to train. You use linear regression, you use logistic regression, you use ridge regression, you use lasso regression, you use support vector machines, you use clustering, you use supervised machine learning, you use unsupervised machine learning, you use reinforced machine learning. I don't care. Now, you have trained your model. Now you need to check the errors. First, you need to check the predictions, and then you need to check the errors. While checking the errors, you need to again cross-validate on the test data. At this point, you'd understand if it is an underfitting or overfitting. If it is underfitting, you go with generalization concept. If it is overfitting, you go with regularization concept. Meanwhile, you also need to know about mean square error, root mean square error. Okay, this is what it is. Now, regularization model help to solve overfitting problems in machine learning. That is one thing. Now, if you're, for example, let's say my model is very poor. If a model is very poor of generalizing, guys, very simple. Generalizing is nothing but it is not putting it efforts to learn from the data and giving you the generalized errors. It's so lazy. That is generalization. Whereas regularization is about it's complex. The machine has done a complex amount of work, but it is adding a penalty term. I mean to say it is adding something else that's not needed, which is causing the problem. Now, how can you control this feature that is causing a problem is called regularization. Again, this regularization is nothing but the parameters. What is the parameters? Your lambda, your theta, blah 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 blah. Okay, that is the regularization. If you don't understand regularization, then I rest my case and I'll have to stop this class right now here, because rest of the slides are all depend upon generalization and regularization. For example, your coefficients is one standard example of regularization. Simple. Again, if somebody asks you about regularization, tell them, boss, my model is so complex that it is overfitting the data. I have to add a technique. Okay, that technique is nothing but adding an additional penalty or adding an additional feature such that it can be an error function. Simple. If you don't understand this, let me know. I'll try a different direction. But if you mess up with this one, your hard work of all these days will confuse yourself and you tend to take a different approach. Okay, that is regularization. Now let's work about regularizing the linear models. Okay, now as we saw earlier, a good way to reduce the overfitting a good way to reduce the overfitting is to, in linear model, constrain the complex model. It is hard for a model to overfit the data if it has less degree of freedom. That's the first example in linear model. Example, to regularize a polynomial model, reduce the number of polynomial degrees. Okay, in a linear model, the regularization is achieved by constraining the weights of the model. When I say constraining the weights of the model, you are adding a penalty term in terms of a cost function that can bring down your complexity a bit down. Now, there are different ways how you constrain the weights. That is nothing but ridge regression, lasso regression, and elastic net. This is what we are going to discuss. Do not confuse yourself. Linear regression is one different model. Logistic regression is one different model. Random forest is one different model. But when you have a complexity in your model that it is really stressing the data so much such that your data is overfitting, you need to regularize it. How do you regularize it? You regularize it by different ways: constraining the weights, reducing the weights, or adding a penalty term in form of a cost function. That can be achieved by using ridge regression, lasso regression, and elastic regression. Okay, that is what it is. Perfect. Now let me go to different performance objectives. Here again we are coming to mean absolute error. Mean absolute error is very important to understand what level of errors are coming up. When you understand what level of errors are coming up, then you can understand what level of complexity is there. When you understand what level of complexity is there, you can understand what level of adding weights is required. Right now, here, if you understand, guys, I'm actually approaching this course in a proper, practical, real-time recommended process. So if you understand this, all your journey will be smooth. But still, I know people are totally new to the world of IT as well. I'm here to help you all, but please do not lose the grip and flow. If you if you lose the grip and if you lose the flow, then this course won't help you. Now, let me give you 1 second. Different performance measures. Now, we have already looked into root mean square error as performance measure. We have really deep dived a lot on it. Now, root mean square error is generally preferred performance measure for regression task. Very, very important. I want you to make a note of it. Root mean square error is generally preferred for performance measure on a regression task. Okay, but in some cases, we want to use another performance measures like MAE, which is called mean absolute error. Okay, this is also called as average absolute deviation. MAE is particularly useful when there are many outliers. Now, again, guys, root mean square error, we already discussed about it. Apart from root mean square error, however, root mean square error is used in the root mean square error is root mean square error is used in the logistic regressions. Okay, or sorry, regression task. But in some cases, you may want to use mean absolute error. What is mean absolute error? The mean absolute error is nothing but it is like mean absolute error, also called the average absolute deviation. Mean absolute error is particularly useful when there are many outliers. Okay, that is what it is. Now, let's jump further into understanding the models. Okay, look at this diagram, guys. You'll understand what is MSE, what is RMSE, and what is the distance. Now, both root mean square error and mean absolute error are the ways to measure the distance. What distance? Between two vectors. What is a vector and what is a matrix? If a letter is in small case with bold, that is a vector. If an alphabet is represented in a capital letter and bold, that is a matrix. Now, do not confuse between vectors and matrix in machine learning, because that is what that drives your understanding towards approaching the project. Okay, so please, you need to be very aware about vector and matrix. I would like to revise once again. Vector is nothing but that is a linear algebra term. A vector is a collection. A vector can be a group of numbers, and a vector is also called as a future vector because the values in the future will be correspondent to some futures. Okay. For example, if you ask me, if you ask me, you know, classify an apple, I'll classify it. If you ask me to classify an orange, I'll do it. If you ask me to classify a banana, I'll do it. Okay. This is called a vector. The vector is also termed as feature vector. Okay. Now, let's take an example of apple, banana, and orange. Now, how do you differentiate a banana and orange? Banana is long in shape, orange is circle in shape. Now, what is the second differentiation? Orange is in orange color and banana is in yellow color, right? Done. Now, these are the features. You are labeling it a fruit that is long and yellow color is an banana. A orange circle in shape and in orange color is an orange. And an apple is kind of circle, but it has a kind of slope on the top and the bottom. This is apple. Apple is red in color. Now these are called labels. Okay, according to the features, you labeled it. You labeled one as apple, you labeled one as orange, you labeled one as the banana, right? Now, like this, the way I told you about a fruit, this will have a corresponding future vector. When I say future vector, again on the go, there are several other things machine will learn by itself where it categorizes. Yes, you are the one that will help me to do a better prediction. Please come and join my family. That is called future vectors. Okay. Now, Kishore, did you understand this clearly? Did you understand the term correctly? Kishore, are you there with me? Perfect. I understand. Yeah, you're right. You're right. You are with me. Thank you. Now, when I say distance between two vectors, again, vectors is future vectors. What is future? Distance. Now, when I say both root mean square error and mean square error are ways to measure the distance, banana length is height, orange length is less height. Now, the way how model classifies is the top, the length
Let's take this way. Okay, guys, I'll tell you practically so that makes sense. This is my orange. This is my banana. Okay, banana is never straight, it has a curve. Now, this is the height of this device. This is the height of this device. Now, your root mean square error is nothing but distance between the vectors. Vectors is again feature vector. Height is one feature. Color. This is red. This is yellow. Again, when I say color, this is categorized into RBG flavors. RBG, not RGB, it's RBG. RBG is any color image is represented in the form of RBG. So distance between RBG and YRBG is classified in the mean square error and mean absolute error. Now, here again, one thing you need to remember is the predicted values vector and target values vector keeps changing every time. Okay, and your root mean square error and mean square error is able to find the distance between the predicted values vector and target values vector. Super. There are various ways distance measure or norms to calculate distance between two vectors. That is Manhattan norm and Euclidean norm. Now, red, yellow, and blue paths, if we can only travel along orthogonal city blocks, is called Manhattan distance. Green path is Euclidean distance. See, green is straightforward. No kutra, nothing. Straight. This is nothing but the Euclidean distance. Right? Now, what is this red color? What is this blue color? So the green path, this is the green path. That is Euclidean distance. Like this, we need to understand how each and every other thing works. Okay. Now let me jump back to pointer, erase all the drawings, go back to the pointer. Now 75. So L1 norm, L2 norm, and LK norm. Okay. Again, these norms are nothing but the parameters, the regularization terms that controls the parameters. Okay. L1 norm is all about computing the sum of mean absolute errors corresponds to L1 norm. This L1 norm is denoted as the symbol I've shown you. This is also called as Manhattan form. L2 form, again, the when you are trying to compute the sum of absolutes, you got L1. When you are trying to compute the root of sum of squares, you talk about L2 norm. Okay. Now, denoted as L2 is also called as Euclidean form. L1 norm is called as Manhattan form and L2 is called Euclidean form. Now, LK norm. The LK norm of vector V containing n elements is defined as L0 just gives the cardinality of the vector and L infinite gives the maximum absolute value in the vector. Again, what is a vector? Vector is a feature vector. What is a feature vector? Feature vectors are used to label the product. Okay, that's perfect. Now, LK norm of vector V containing n elements is defined as, you see the formula here. Do not get confused and do not worry about the formula. The formula is so something that runs in the background, but we are not concerned about it. So just remember, L1 form is about mean absolute errors, L2 form is about root mean square errors, and LK form is all about uh, finding the norm of the vector V containing n elements. Okay. Now, L0 gives the cardinality of the vector and L infinity gives the maximum absolute value in the error. Okay. Now, let me jump to next one. Now, LK form is called the norm, the higher the norm index, the more it focuses on large values and neglects the small ones. Super. This is why the root mean square error is more sensitive to outliers than mean absolute error. But when outliers are exponentially rare, okay, like a bell-shaped curve, if the outliers are rare, then root mean square operations performs very well and is generally preferred. L1 versus L2 regularization. L1 can yield sparse models while L2 doesn't. Now, give a thought about what is sparse model. This is very important. Give a thought about what is a sparse model because it's very important. If you don't understand the word sparse model, then you are literally messing up your machine learning model. I repeat, when you are regularizing between L1 form, L2 form, and LK form, L1 form is leading sparse models while L2 doesn't. Okay, the sparse is nothing but it is a kind of regression model explaining the definition what is meant by sparse. For example, let's say you have samples, right? I have 100 samples, 100 examples, or 100 experiments. When this samples is less than the dimension where it has to be taken, that is called sparse. That is called sparse matrix. I'm still trying to think how can I explain this example much better. Guys, I have to show a diagram for this sparse model, but in a nutshell, I'll tell you something in a short. Very simple. For example, let's say you have trained your data on 1 million data points. Okay. When you trained your data on 1 million data points, you'll have 1 million variables or 1 million dual variables. Okay. Now, for any reason in this 1 million things, if you have a non-zero value, okay, then you'll have to find a way how you are going to store this 1% a non-zero value. How you gonna store? Where you gonna store? Now, if you are going to deploy this model on a low memory device, then what is the problem? Okay, that is the sparse. That is a question mark that you have to. You are in an uncertainty. So L1 can yield that level of uncertainty while L2 doesn't. Now, at times, sparse model is complex and efficient because the question it is raising is making machine to learn by itself. Okay, that is the importance of sparse. Sparse will help model in future selection. Sparse will tell which features are important, which features are not important and redundant. Okay, that is what it is. So next one is let's understand the ridge regression, lasso regression, and elastic. I have slides prepared, but I don't have time. Today I have a meeting early in the morning, first hour, so I'll have to start early. I'll wrap up here. We had to waste 15 minutes in the start for the Microsoft PowerPoint updates, and my apologies for that. So we have today understood very clearly about BIOS variance trade-offs. It's not that we not discussed about it earlier. We discussed this as part of end-to-end machine learning without even trying to understand what exactly happens in the background. We just did that to understand the whole flow of the project. Now what we are doing, we are deep diving into what is BIOS, what is variance, what is BIOS variance trade-off, what is BIOS variance trade-off and introduction error. And after that, we understood about regularization. In the regularization, we talk about L1 form, L2 form, and LK form. L1 form is for mean absolute errors, L2 form is root mean square absolute errors, and L1 forms a sparsity and L2 doesn't do it, but you still have an advantage in sparsity is it helps you to understand which feature is important, which feature is not. That's what I learned today. And tomorrow we'll understand about ridge, elastic, and lasso. As I told you, these are not exactly the models. These are the models that will help you to reduce the constraints and weights of the models. Okay, that's what it is. Guys, my sincere advice, if you don't memorize, if you don't make a note, then you are screwed up. You are badly screwed up if you don't maintain the overall flow by yourself. Take a big white paper in your hall, write down all the crap you think is right, come back to the slides, refer it, go and correct it, and put the right version of the thing in your hall. When you are watching a TV or when you're in the hall, I want you to look at that sheet you attested to the wall. That way, in your subconscious mind, you're training your mind to look at it and understand the flow. Just do some smart things. That's all. Okay. That's all I have for today. Thank you, Kishore. I appreciate your commitment. I appreciate your patience. Please join me tomorrow workshop. Please try to come early. I'll reach there by 9 because the fob and access is with me. So we shouldn't delay. Every minute is important for us. Kishore, you and Srija have to stay long because we are working on some advancements for you. So please plan accordingly, get food or, we can go out still, but what happens is it's quite long and we just have to waste 30 minutes to go out and come back. So plan accordingly. I'll see you tomorrow. Thank you so much. Have a great weekend.